Okay, welcome back. So good afternoon, everyone. My name is Marius. I'm an assistant professor in statistics at the University of Waterloo in Canada. And I'm a bit of a mixture between a statistician, a probabilist, and a computer scientist. This afternoon, I'm going to be the computer scientist, mostly, 99%. So I will give you a small introduction, very small introduction to R, where you can find sources and help and these things. And then I would like to use R as a vehicle to show some things you learned this morning to you in R. And this is really why we want to use R. It essentially gives us another possibility of digesting, of learning the things we discuss in terms of formulas, in terms of mathematics and probability theory. So this is going to be the plan. So I was a witness of an active discussion during the lunch concerning differences between Python and C++. And so I know you are a very diverse group. The variance is quite large. That might even more so apply concerning R. So I'll do my best to kind of set the level right for everyone, but it's not going to be very easy, just to warn you. So. Yes. So that was my first question. How many of you have used R before? Okay, fantastic. How many of you have written functions in R using for loops? Okay. How many of you know what lapply is? How many of you know what vapply is? Aha. And how many of you have written packages yourself? Okay, good. Okay, great. So I'll try my best to make it right for everyone. So the first.
There's a missing question. Who's never used R before?
Yeah, okay. Of course, that's all. Yeah. Okay, good. Yeah. Okay, so the first question. Why R itself, right? So for us, it's free. It's freely available. That's fantastic. That's one part. Computation-wise, it has a lot of statistical tools, right? This is what we need. I don't need to implement my own goodness of fit test in C++ or something like that. So all these tools are available. And then graphics. Graphics is very important for us because we mostly want to visualize things. And that's maybe the biggest message I would leave to you with this afternoon, that you see how much you can extract from a nicely made plot. You can see much more than from a table of numbers or single numbers. You always want to plot functions and learn from the behavior. And then it's higher level than other programming languages, which is great. If I want to optimize a function, I can simply use the optimize function or optimization under constraint. There are functions available to do that. I don't have to do this on my own. And there are lots of packages available that implement all of these tools I might need at some point. There are close to 9,000 packages at the moment. There are far over 100 submitted every week. There are close to 100 published every week. So there's this huge database of packages we can make use of. And if you search for something specific, it's quite likely that there's already a package. It's also very likely that there are more than one packages that do the same thing. So you will have a lot of packages available. Where to find R? So the main R website is the one you see on the right side, so of the R project. The one you most likely want to go to is the CRAN or CRAN website. I call it CRAN, some say CRAN. So this is this website where you find a lot of information about R and sources as well and so on. So for example, not many know about task views. So if I have the problem of, let's say I want to do time series modeling, as Alex will do later today, then I can go to the task views and I see a lot of packages described here. I roughly get an overview of what's available, what I can use. And for example, I see the Rugalj package somewhere. At least it was here before. Let me just search for that. Yeah, so I see the Rugalj package, and that's the one we were going to use. Yeah? So you get a nice overview of what's available. Also, there's a task view on optimization, for example. If you have optimization under constraint, you get an overview here of the packages you could use. So task views are very helpful. And then you get, of course, the R sources to install, or binaries as well. So I think that's maybe not so interesting to go into detail here. But then the packages. Yeah? So you can get an overview over all the packages, and for example, you can look into, let's say, the QRM tools package, or just search for QRM and see what's available there. And then once you click it, you see an overview over the package. You see the current version, when it was published. You see what other packages it relies on, or what other packages it uses every once in a while. You see the corresponding maintainer, so if there's a problem, you can write to the command maintainer and then the package name, you get the current maintainer of the package, and so on. Yeah? And then you also get a manual here. And that manual is essentially a PDF with all the help files in R, so you can jump to a function and see what it does. Yeah? So for example, we will use the risk measures later today, and there you see there are some risk measures implemented here. The one we currently use is not in here yet, yeah? Because the package is just started essentially and is under heavy development. Yeah? So I think the last update I did was on Saturday or so. So be aware that if something does not run because you're missing the function or anything, always get the very latest version of the packages, and R itself as well, ideally. Yeah, so you see the functions that are there and the arguments, and I'll look into that a little bit closer soon inside R then. Yeah, so you get that overview. You also get vignettes, and vignettes are simply HTML files that give you a nice overview of certain aspects in the package. For example, one of the vignettes here is about fitting and predicting value at risk based on Arma-Gauge processes, so a little bit of a mixture between what Rüdiger did in Chapter 2 and Alex will do later. Yeah? And it's a very nice HTML file. You can extract the code. You see a lot of nice plots and so on. Yeah? So many packages have vignettes by now, and they give you a very nice overview over certain aspects. Now you also get the package source. So if you really want to know how something is implemented, for example, one idea would be to download the package source and then change in that directory, unzip it, and then look inside, and you get all the possible functions in there and so on. Yeah? Help file as well. Good, so there's there are a lot of things there. There are also the manuals. Yeah? I can particularly recommend two: An Introduction to R. It's a good manual if you haven't worked with R before. And then there's the Writing R extension for the professionals that also do package development. What else is there? There are the FAQs there. Yeah, you read through them. There are some really nice ones. Especially the 2.7 is a nice one that tells you how to get help about R. Yeah? So there's an overview about the possibilities how to get help on R. Then you had the manuals, as we just discussed, for getting help on specific functions, yeah? Inside certain packages, for example. You have the task views, which we already discussed. You can simply use Google with R help or something like that, yeah? R-help typically, and then what you're looking for, that typically leads you to some answers. There are also specific R-related search engines, if you are interested in that. And there's an R mailing list. R help is the general mailing list you can subscribe to and get news about R and interesting questions and so on. There's Stack Overflow, you might have heard of. There you can post questions and other people can answer. That typically goes very quickly. If you have a good question, then your question will be upvoted by others, so you also get points for asking good questions. But these are non-trivial things, so if it's answered somewhere else, they go after you. Yeah? So don't post trivialities there, only good questions you couldn't find the solution of. Then there's the R graph gallery. I already opened it earlier here. That just shows what kind of nice graphs you can make with R, all sorts of different graphs. So let me just give you one example here, and you can go inside, and then you see the graph, and you also see the R code. So if you see a plot and say, hey, that's actually something I want to have, then you can see the R code as well, and you can learn from that. Then our bloggers, that's a blog about R in general, and you find very nice things that people have done with R, and yeah, so that's more generality there. Then, of course, this is all externally, right? So internally, from within R, you can also get help. Let me just do that here. So I start an R process, And let's say I want to find the root of a function, and I don't really know how this works, but I heard that I can use the uniroot function, so I use !uniroot, and I get the help file of the uniroot function. And so this is essentially what you've seen before in the manual as a PDF. Yeah? So you see the function, you see its arguments are explained here. It's always the same structure. You see details about a little bit about what's going on underlying or what to take into consideration when using this function. You see the return value explained. What is it? Here in this case, it's a list of different things, and what does it contain? The root, the function value at the root, and so on. Yeah? And possibly references to the underlying algorithm, sometimes also who implemented it, and then examples. And those examples are typically helpful. You can just execute them and learn from that. So essentially you see here, I executed that example. So this is my function here, and I compute the root of that function, and here this is the corresponding output. So it's extremely helpful to learn from these examples at the bottom of the help files. So that's typically the way to go. Now, how can I work with R? Most of you probably work in RStudio, and that's also something I would recommend. Alex uses RStudio as well, for example, later on. So you see the GUI interface, the browser interface of RStudio. I work in a slightly more specialized way with Emacs and ESS. That's helpful for package development. So that's kind of my setup you see at the moment. The idea overall is that you write a script. A script is a file with ending .r, yeah? And in there you have the commands. You then execute line by line or paragraph by paragraph and so on. You can then also send the script to a different computer if you like, to execute it in parallel, for example, if you have a bigger simulation study involving certain risk measures, computations and so on, or time series modeling and things like that. Yeah, but if you start with just a script with ending .r and have the commands in there, you can typically, in all sorts of GUIs available, step through that line-wise, and then you see the output, and that's typically the way to work with R. Now, how to install, as I said, install R itself. You can look up on CRAN, of course. Installing certain packages works with the install.packages command from inside R. Yeah, so if you need QRM tools from CRAN, then you do install.packages, quotation marks, and then QRM tools. Yeah, so that's the package we will use today. And if you need the very latest version, because you saw on CRAN it was not updated since end of May essentially, then the latest version you always find on the development server, which is RForge. Yeah? And so if you want to install the very latest version, by the way, this is also mentioned on the website, so you don't have to take down notes here. Then use install.packages, QRM tools, but then repos, specify the repository. Repos equal to, and then that's the website or like the server side of RForge. Yeah, so that's the one you should use then. Then you get the very latest version. Good. Now, the scripts we present to you, they are all available as well. So how do you get those? So you go to our website, the QRM tutorial website, Paul already mentioned. So there you find a lot of things. For example, here would be the full set of slides Paul mentioned earlier today, and then the R code would be available here. So here you find, according to the different chapters, the corresponding R scripts. Now, at the moment, it's a bit tedious to download all of them one by one. If you want a complete repository, just click on Complete GitHub Repository, and then there's this button that says Clone or Download. And if you click here, you get the whole repository, and that even includes the full set of slides, if you like. So this is how you can work with it. And the script I actually have open at the moment is this first one. So one, an introduction to R programming. So this is exactly that script I've currently open. Good. So this script takes about 80 minutes and gives you an introduction to R. Obviously, I'm not going to do that. So execute that line by line and learn from it. There are lots of comments in here already explaining things like division by zero and certain problems of this type. and go through it on your own. It's a very good exercise. There's just something I would like to very quickly point out to you further down, namely random number generation. We very often generate random numbers from certain distributions, and I would like to very quickly give you a little bit of an overview here. So now I am starting a new R. Let me just start a new R process here. So you see that process down here. And I generated 2 random numbers from a normal distribution. Now, what R does, it generates a seed. Yeah? There's no such thing as randomness on the computer. There are only sequences that mimic randomness. Yeah? And pseudo-random number generators do exactly that. They walk along the sequence and give you the random numbers. Yeah? So this is essentially what's happening. And the reason why I mentioned this is because for generating from the normal distribution, the method that R actually uses is the so-called inversion method. You see that here. And this inversion method, you will see that again in chapter 7 tomorrow afternoon. This inversion method works as follows. So it essentially uses value at risk, or the quantile function, to generate random numbers. So all you need to know is how to generate from a uniform distribution on 0, 1. And this is done in a very complicated way in the so-called Mersenne twister. There are other pseudo-random number generators available. But this is virtually the only thing that the computer really knows well how to do. And then to get, let's say, a Pareto distribution or a normal distribution, you apply the corresponding quantile function to that U. Yeah, so essentially, our value at risk at this random confidence level, if you like. And this then turns out to be a random realization of a random variable from that distribution F. Yeah, and the proof is very simple one-liner. Yeah? So you just show that this new random variable is indeed distributed according to F. Yeah? And all you do is you bring the quantile function to the other side. And this is absolutely a crucial step in understanding also the multivariate case, which you will then learn in chapter 7 tomorrow. Yeah? But the reason why I show this to you is that you all know that the univariate, the normal distribution function is not explicit. The normal quantile function is not explicit either. But still, R uses exactly that method, inversion method, which you see here, to generate from it. Yeah? And that's something on the technical level I think is important to know. Yeah, because we can approximate the normal quantile function to such a precision and in such a fast way that this method is feasible. Yeah? So this is something interesting to know. And then, of course, if I generate 2 more random numbers, you see I get something different, different than before, obviously. Yeah? But I'm interested in reproducibility. I would like to be able to reproduce a certain result. Yeah? So that's why I need to set the seed. I need to specify where in that sequence of random numbers that look like random numbers, but are actually not random numbers, where I am. And once I specify that seed, I know which random numbers are produced next. So if I first set the seed, draw 2 random numbers from the normal, and then set it again to the same seed, so essentially go back along that sequence and draw again 2 normals, then you see, aha, they are the same. Yeah? Now, why did I use all equal here and not equality signs? Yeah? That's a small exercise for you. Look up the help file of all equal. Very good to know, that function. So that's small homework for you, so to speak. Good. So this is all I wanted to do here concerning the introduction. Now, I want to do a little bit in R concerning value at risk and expected shortfall estimation. Yeah, so I've learned this morning that, okay, so Rüdiger told me that, okay, value at risk is essentially the quantile function, and then expected shortfall is essentially the mean of overall losses that exceed value at risk. Yeah? So if I have a bunch of losses, then my empirical distribution function looks like this. I jump by 1 over n, if I have n losses, at the outcomes, at my losses, right? At each loss, I jump by 1 over n. So I have a step function. So, so non-parametrically speaking, if I don't want to assume a certain model, this is the best I can do. I can replace my distribution function here by the corresponding empirical distribution function, or the quantile function by the empirical quantile function. Yeah? And the way this then works is simply, I have a certain confidence level alpha, and then I go over exactly in the way that Rüdiger showed us this morning, and that's going to be my corresponding value at risk based on this empirical distribution function. So it's my empirical quantile at the level alpha. So this I could use as an estimator. And then I could simply use that estimator in here, right? So I plug my estimator in here, and I average over all losses exceeding that estimator to get an estimator of expected shortfall. Yeah? So expected shortfall estimator at level alpha would be that. Yeah? But I want to compare the two and want to investigate how is the variance of that estimator, for example. How do I compute this? Is it really true that my value at risk estimator is smaller than my expected shortfall estimator? These things. So in that we will look at now. So there are lots of comments here about how to derive these estimators and so on. You don't need to know the detail at this point, but if you like, then go back and read in the script. And I take 2,500 losses, so about 10 years of daily data, which is, of course, a lot, but still, yeah. So this is what I do at the moment. And then I would like to repeat this estimation procedure 1,000 times to see how these estimators perform. And as the true underlying distribution, as the true loss distribution, I assume a Pareto distribution with parameter 2. The Pareto distribution has this distribution function. I put it down here. Yeah? And yeah, so the quantile function is very explicit too, and I can use that to simulate losses from the Pareto distribution with the inversion method we just discussed. And that's going to be my losses, and then I do non-parametric estimation of value at risk and expected shortfall based on these losses, and then I resample these losses 1,000 times, and each time I do value at risk and expected shortfall estimation. So instead of just one estimator, I get 1,000 estimators, and then from these 1,000 estimators of value at risk and expected shortfall, I can then compute or approximate a variance. I can compute confidence intervals and so on. The technical term behind this is known as the non-parametric bootstrap. And the full version of the slides has a bit of around that in the appendix if you're interested in more about that.
So you're basically doing a simulation with 2,500 points, and you
yes.
repeat the simulation 1,000 times.
Yes, correct. Good. So
couldn't you just do a long simulation of 2.5
that's
years?
technically the same, obviously, yeah. Yeah. So I see. That would be yeah, okay. Instead of generating 1,000 times 2,500 resampled losses, if you just generate 1,000 times 2,500 losses, that would indeed be different. Yeah? Because here, this is the non-parametric bootstrap. Yeah? So there, it's different. I resample the same data. I do not generate more data. So this is a realistic setup. Yeah. There's a lot going on here. Yeah. So stay here. That's important. Stay here. There's a lot going on here. Good. So let me set the seed because I want this to be reproducible. If you go home and you do this and you get a different result, you blame me. So that's why I set the seed so it's reproducible. And then I generate my base losses from the Pareto exactly with that inversion method. Yeah, so I apply the Pareto quantile, Q par, to N, to my 2,500 uniforms with Pareto parameter 2. And the confidence level I look at here is 99%, and I compute the non-parametric value at risk estimator and expected shortfall estimators. And so you see you get 8.16 and 13.42. And those are just two numbers I can believe or not. I don't really learn anything from that, right? It's just single numbers. What I would learn from a little bit would probably be to look inside the R function and see how it's defined. And you see my value at risk is indeed just the quantile function, the empirical quantile function at my alpha confidence level, so there's not much going on. Yeah? And my expected shortfall is simply essentially taking out with an indicator all losses that exceed my value at risk estimate which is computed here, and I take the mean over them. Yeah? I do this in a vectorized way. You can feed it with several confidence levels at the same time and so on. So it's slightly smarter than that, but that's essentially what's happening. Good. Now, what could we look at? Those are just single numbers. Aha, functions. We want to do functions in the confidence level to see the behavior of the estimate. So here and we are especially interested in large alpha. So what I'm doing is I concentrate the alphas near 1 with a sequence 1 minus 1 over 10 and then some power. Just to make sure they are all in between 0 and 1. And then I evaluate valued risk and expected shortfall. Aha, there were some warnings here. Aha, there were some cases where there were only 5 losses bigger than valued risk, 4, 3, 1, and so on, down to 0 losses. Yeah? And this is clear. If you think about, we have only a finite number of losses. Once my confidence level is too large, my valued risk estimate is going to be the largest loss. And then what do I have left in the tail? Nothing. Yeah? So all my losses strictly exceeding value at risk, how many do I have? None. And here you already see the difference between the theory and practice. In practice, it does make a difference whether I have equality here. Yeah? Because then I would get a number. If I have equality here, then I would always, for sufficiently large alpha, I would always average over the largest loss, and at least that would give me a number. Now, I chose to use strict inequality here so that you don't, but there are no losses exceeding, so the estimator simply cuts off. So it does make a difference. And that's also a bit the challenge when working in the software. So in theory, I have a real line. On the computer, I don't. So that's typically the problem. Good, so I have these estimators. And I also have the true ones for the true underlying Pareto distribution. Very good exercise, do that. Compute value at risk, expected shortfall for the Pareto distribution. Yes, a question? That's a different story. Of course, there are, you can do a lot there. But yeah, I just fix it large enough at the moment. It's not the point we are interested in at the moment to know how large I should choose the number of bootstrap replications or anything like that. Yeah. Good. And then I plot all the computed values so far. So the true valued risk and expected shortfall and the corresponding estimators. And if you are very honest, then you blame me now and you say, I don't see anything. Yeah? And that's true. And please don't try to see anything from this picture because it's not possible. Yeah? You see it's for large alphas we are interested in, it's suddenly increasing very steeply. You don't see that interesting region we are interested in. So what could I do? I could scale down these losses here to see more what's going on here. Yeah? So I could use a logarithmic y-axis. And then I already see a bit more. For example, I see, well, both of my estimators are increasing. That's what they should be. I see that my value at risk estimator is picking up the true underlying value at risk quite nicely. The expected shortfall estimator has more difficulties. Why does it have more difficulties? Because it needs to consider the whole tail of the distribution and not just the quantile. So it has slightly more. You can also say that you can also kind of already expect that the variance of this estimator will be larger. But I'm still not happy here because I still don't see the full picture, which is for the really large alpha values here. So what I could do is I could also use log scale on the x-axis and then plot it in 1 minus alpha. That's, by the way, exactly the plot that Rüdiger showed you this morning with the normal and the t model. In log scale, they have value at risk being larger or smaller than for the normal versus the t. And that script is online as well, so you can reproduce that. So I plot it in 1 minus alpha and in log scale. And suddenly I see a bit more things. Yeah? So I see that my value at risk estimator suddenly is the constant only. What is that constant? What is that constant? Question for you. Can anybody help me here? Why is my value at risk estimator suddenly constant here? And what is this value? Yes, very good. It's my highest value, exactly. Because for sufficiently large alpha, I will always return this largest value. So I can actually read off my largest loss in this plot. Yeah? And I'm going to be flat because I have a step function. Good, and then my expected shortfall estimator would actually be the same if I used equality here. Then I would simply average over the largest loss, which would be the largest loss. But it drops off here because I have the strict equality here. But I also see that the expected shortfall estimator is off from the true underlying value much earlier than value at risk. So it is more difficult to estimate expected shortfall than value at risk, at least non-parametrically. And all of what we do here will motivate very much parametric or semi-parametric estimators you will learn about tomorrow in EVT. So the non-parametric estimators are by far not the best ones. But I think it's a very nice example for you to learn what you can do with a nicely made plot in R to learn about the theory and the practical applications of it. So you can take away quite a bit of this interaction, and you can play around in R. That's the nice part. And of course, the true underlying quantities, they don't cut off. You have a continuous distribution there. They're just there. But you see, this is definitely a region of alphas we are interested in, and you see how far you can be off, essentially. Now I want to, I have this one sample of size 1,000, of size 2,500, and I computed these values, value at risk, expected shortfall, as functions in alpha based on that very same sample. Now, in order to get a notion of a variance or a confidence interval around that, I could resample the data. So I just assume that's my data. I assume I don't know anything. I don't assume I know the underlying Pareto, right? I just kick this out of the game. And then the best I can do is I believe that my empirical distribution function underlying based on the losses is my true underlying distribution function. And if I believe that, I have to resample, I have to sample from that empirical distribution function. And what this does is just resampling from the data. That's what it means. And so I resample 1,000 times from those losses with replacement. And then each time I do exactly that. I compute value at risk, expected shortfall estimator, exactly in the same way as we did here. And then I can, based on, for each alpha, I have then, instead of just one estimate, I have 1,000. And I can cut off the lower 2.5%, upper 2.5% to get a 95% confidence interval. I compute for each alpha the variance over these 1,000 values as an approximate variance estimator of the non-parametric value at risk and expected shortfall estimators. And I can still plot everything in a single plot then. Good, so let's do that. So I need to bootstrap everything here. And then, of course, for small alpha, I slowly run out of samples above value at risk. So here you see the number of the percentage of NAN, so not a number I get from the expected shortfall estimator if I increase my alpha. Yeah, you see around 99.9% roughly, you see that I have less and less observations I actually average over. That's of course critical. Yeah? It doesn't make sense if I don't have any losses anymore to average over them. But yeah, that's just for me to see what's going on here. And then in the end, what do I get? I get a large plot in log-log scale, and which contains a lot of information here. So essentially, the true values of value at risk for the Pareto distribution and expected shortfall, the larger line here, the line above the value at risk. And then I get my estimators. So those are the dashed lines. Yeah, so those are the ones you've seen before here. And then here for expected shortfall, the red one, cutting off here essentially. And then I get confidence intervals around them. They're not too reliable because I have less and less observations as I go along. But still, you see, for example, that the confidence intervals around expected shortfall are larger than the ones around value at risk. Yeah? So that's roughly visible here. And you also see what the variances do. So first of all, the variances increase as alpha increases. So the larger my confidence level, the larger the variance of my estimators, which is of course a bad thing. I also see that the expected shortfall has a larger variance overall than value at risk. So I have to expect higher variances if I estimate expected shortfall than value at risk. Yeah? Again, I look into the whole tail, not just a single quantile. So those are the types of observations you can take away from here. And so this is very nice exercise overall, I think. As I said before, you have all the results I just mentioned down here again as a comment. All of these scripts we have available online roughly work similarly. So you see you have a lot of comments there you can read through. And so that's it from my part. And Alex will show you some more scripts, and we'll continue with chapter 3 then.
Okay, so we're going to move on to chapter 3, which is called Empirical Properties of Financial Data. And it would seem natural to immediately look at financial data if we're going to talk about empirical properties. So Marius has given you the fundamentals of what R is, where you find it, although I was pleased to see that a lot of you already know it. Some of you don't. And for those of you who haven't seen it before and you're wondering what system to use, I'm a little bit less hardcore than Marius, so I'm going to use RStudio. And so you'll see RStudio. That's the big white window in the background. If you've cloned the repository, as Marius suggested, that's going to be the easiest thing to do. If you want this code, go to QRM tutorial and take the zip file, which is the whole repository. And in the R directory, you're going to find this subdirectory structure. And so we're going to go into chapter 3. And there is there's a script in there called Exploring Financial Time Series Data. Let's see. So you see it here. Empirical Properties, Exploring Financial Time Series Data. So that's where I'm going to begin. And let's see how that is for size. How well can you read that in the back row? Would you like a slightly bigger font size, or can you read the first thing it says in blue, Library XTS? It's okay. Don't hesitate to tell me to blow it up a little bit. But the smaller we keep it, the more you can see in one window. So the more you see of what's going on. So this is RStudio. There are 3 panels here which are going to be active. My pre-prepared script is up here. And commands I execute will be echoed down here. Over here, various things will appear. And one of the first things we might look at in RStudio is the list of packages. So there is a list of packages here, which I have available. If the box is checked, that package is already installed. But I'm going to need 2 further packages for my presentation of this chapter. So let's begin with Library XTS. This is a time series library. We're going to spend the rest of the afternoon essentially looking at time series. So XTS is extensible time series. It's not my work, it's not Marius's work, but we only recommend what we think are good quality packages. If they are being entered on the repository at the rate of 100 a day, it's fair to ask whether they are all uniformly wonderful packages. There is a certain amount of quality control, but we're relatively sparing with the packages we use. So XTS, I think, is the top times. You'll see if you look at the task view, Marius showed you the task view, you will see that there are many time series packages, but we've gone on to XTS. The next library is one of ours, so QRM data. And let's have a look at what's in QRM data. Okay, data sets for quantitative risk management practice. This is my effort and Marius's effort, actually more Marius's effort than my effort. I said it would be nice to have some data. I said I would settle for a few exchange rate time series and a few stock index time series and a few stock price time series. I said maybe we should have some Dow Jones stocks. Mario said, well, let's have them all. I said maybe we should have a few Standard & Poor's stocks. Mario said, well, let's get them all. Going back from, well, this version of the library goes up to the end of 2015. So it's not real-time updated, but this is historical data to play with up to the end of 2015. The intention is that we will update the repository yearly. We had to ask special permission to update the package yearly. We had to ask special permission to have this package because it's considerably bigger than the standard default package size. But in here, what you will see, foreign exchange rate data, stock index data, what else? Some commodities, the gold price, oil price, some volatility index data, just lots of things to play with. Some interest rate data, which will be the subject on, or one of the subjects on Wednesday morning. So in this script, we're going to look at some of it. So for example, this one here, DJ const, that's the Dow Jones constituents. So we'll have that. And immediately, a command that many people like to use to get an overview of what an object is. Everything is an object. DJ const is an object. It is an XTS object. It's an extensible time series. You can see the date range, 62 to New Year's Eve 2015, and other more cryptic information that true R enthusiasts will be able to interpret to some extent, but I won't go into. So some of the basic things you need to do, you always want to pick out time periods. So for example, we will pick out the time period that goes from the end of 2006 to the end of 2015. So that basically the 29th, that gives me everything basically in 2007 and up to the end of 2015. It's a very natural syntax. You just put the date range in quotes and we'll take the first 10 stocks. So I'll pick up the speed a little bit here, and we'll plot them. Plot zoo. It seems like a strange name for a command. Plot zoo. A zoo is another kind of R object that is intended for data with a natural ordering. Time series of a natural ordering in time. And plot.zoo, that shows us the first 10 Dow Jones constituents. When we talk about the empirical properties of data, we will look at returns, return data. And by default, we will generally take, I think we will almost always take log returns. And so there's no point in having a function to compute log returns. Log returns are log differences. Take the log of the value, difference it, and then there's just one little twist here. Because if you go from a time series of length n, if you difference it, it becomes n minus 1. And when you apply these operations to a time series, it returns something of the original length, but the first observation is NA, so we just remove it. So don't worry about this minus 1. Every time we take a log difference series, it will appear. So dj.x is the series of log returns. There were 10 stocks. Head gives you the first 6, and so this is the first 6 of the last 4. There's Walt Disney and Goldman Sachs. These are log returns. And again, plot zoo. These are the kind of time series we want to discuss in this chapter 3. They show something that we will call informally volatility. I think that's quite clear. Anyone remember the year 2008? There was a lot of volatility in late 2007, 2008, into 2009. We remember that as the financial crisis. Although interestingly, I now teach MSc students who are young enough that they don't really remember that very well. It's very fresh in our memory, I think. So we see volatility. We'll have to describe that mathematically in some way, but it's the sort of thing, you know it when you see it. Volatile periods and then quieter periods later on. Another thing we're going to want to do a lot is change the time frame. So in QRM data, largely we have daily data. In fact, I think most of the time series are daily data. Not higher frequency. We really would have problems putting a big high-frequency database on the CRAN archive. And not lower frequency, because of course we can construct lower frequency from our frequency, daily frequency. And it's very easy to get weekly returns, monthly returns, quarterly returns, yearly returns. In the XTS package, there are these commands apply weekly. Now, the nice thing, or one of the nice things about log returns is if you add them up within a week, you get weekly log returns, or if you add them up in a month, you get monthly log returns. So in order to get my weekly returns, I apply weekly summation. I sum all the columns. I use the function column sums. Obviously, I reduce the quantity of data I have by doing that. I don't think we looked at the size of this data, of the daily data. So I'll just type that in the bottom. So we started with 2,266 days, and then of course you sum them up within weeks, and we have 470 weeks. Those are the weekly returns. You still see the volatility in weekly returns. I can compute monthly returns. We have 108 months. 108 months, those are the monthly returns. You still see volatility in the monthly returns, and so on. Apply quarterly. There are 36 quarterly returns, so what do we have? We have 9 years of data, and those are the quarterly returns. So that's just some stock data. And just to show you a few more stock indexes, what shall we take? Well, we'll take the S&P 500, the world's biggest financial market, United States. We'll take the FTSE. I work in the United Kingdom, in Edinburgh. And of course, we'll take the SMI. You can look and see what you've got here. The S&P 500 goes back to 1950. And we have the constituents of this S&P 500 going back to when they start, to 2000. Okay, not quite so far. Not so far. We've still got lots of data in there. Okay, that's the S&P 500 since 1950. Sometimes you want to join some time series together. You want to take, for example, the S&P 500, the FTSE, and the SMI, and you want to merge them. And you might start by taking everything you've got, all is true, and having a look at that. So that's everything we've got. We've got less of the Swiss and less of the UK and more of the American. So we might then just merge the dates that we have in common across all the time series. That's all is false. Retain only days where the indexes all have values. And so that's our index data, for example. And so this is just reinforcing the basic things we always tend to do. Log differences. I log difference them all. Let's plot the log differences. Plenty of volatility there. There's 2008 again. Another thing that you'll see us do a lot, pair plots, because tomorrow we're going to, there, it appeared. Pair plots. Tomorrow we're going to get into the multivariate structure of data. Today I will deal with the single time series largely, but tomorrow we will go into dimension D. So quite often we learn things by looking at pairwise scatter plots of each possible pair. Again, we could aggregate those things. I won't bother in this case. Let's just look at a few other odds and ends. Exchange rates. I've taken here the base currency to be the US dollar. You can see the pound. You can see I've taken the pound, the euro, the yen, and the Swiss franc. And I'm going to have a look at those. So all of this is in QRM data. There's the first few values behind me. Here's what those exchange rates look like. Log returns again. Typically, we would look at log returns, I think, to express the way that exchange rates change. So that would be log returns. Remember this event here? It was when the Swiss franc, the dollar. When was that? Yeah. Yeah. So an extreme value there caused by this unpegging, right? Yeah. Yeah. Removing the floor. So, exchange rates. Another thing we have in here, a couple of bond or yield curve databases. So zero coupon bond yields. Perhaps let's have a look and see what the quality of the documentation is like for this one. Interest rate data. We have zero coupon bond yield curves in Canadian dollars and US dollars, again stored as XTS time series. So these are quite nice for exploring the way that yields change for different times to maturity. So let's attach that data. You'll have noticed by now, I think, that to use these data sets, you first use the command data. That makes the data available. Now, the dimension here, this is 6,088 days and 120 different times to maturity. So, for example, if we look at the first 6 lines, and if I spread this out a little bit, you can see that what we have here, we have I need to go back to the start of it. Yeah, what we have here, starting in 1991, in January, we have yields for time to maturity, quarter of a year, half of a year, 3 quarters, 1 year. So it goes up in quarter years to 30 years in this data set. I will change the yields to percentages and plot a few. So let's plot the first 10 times to maturity. So that's going up quarterly to 2.5 years. So these are the actual yields from 2002 to this is a slightly older database. This one ends in 2012. In general, most of the data sets do go up to the end of 2000. No, it's not. No, we do have it up to the current time. It's just that I selected a period. Beg your pardon, I selected that period. We do have them up to the end of 2015. I will take simple differences here rather than log differences. With negative exchange rates, there are problems about taking log differences. So I'll take simple differences, although all of the data in here are actually positive. But I'll take simple differences. I'll pick 3 maturities, and we'll plot them. So this would be daily changes in the yield to maturity, daily changes in yields for time to maturity, a quarter year, 2 years, and 10 years. Daily changes. These are likely to be quite dependent, at least, for example, the changes in the 2-year yields and the 10-year yields. How do I know that? When I look at the scatter plots, I see a lot of positive correlation. I have 120 different times to maturity. If I'm going to model bond portfolios, I'm probably going to want to reduce the dimension in some way. So we will talk about factor modeling beginning tomorrow for reducing the dimension of these kinds of risk factor data. That's probably enough just looking at data. And so I now want to take you back to the slides and discuss some of the things that you've seen in these data in a more systematic way. We call these the stylized facts of financial return series. I don't think we were the first to call these the stylized facts. It's a term that's been around. What is a stylized fact? I find it a very strange term, but it's basically an empirical observation. I'm not saying this is an absolute truth, but it's something that we observe again and again and again without exception. So it's an empirical observation, and logical consequences of these observations which apply to many financial time series of risk factor changes. So you heard in chapter 2 this morning that we deal with risk factors. We called them X. So the risk factors are prices, rates. Later on we'll have things like volatilities, so interest rates, exchange rates, prices, index levels. These are the risk factors, and we're interested in the changes. For many of them we will take log differences. Occasionally we will take ordinary differences. So these stylized facts apply to those kinds of time series. And the time frame I have in mind is daily. So I'm typically thinking of daily, but most of what I say will apply equally to weekly, or to 2 weekly, or to monthly. It may even stretch to quarterly. I'm not going to talk about stylized facts of high-frequency data. So tick-by-tick data would have their own collection of stylized facts, things that we observe. And as for very low-frequency data, such as annual changes in risk factors, well, frankly, we don't have a lot of data to say things about annual changes, because you can do things like make overlapping annual returns. But still that doesn't contain a lot more information than simply taking non-overlapping annual returns. And that maybe introduces a question to me, which I think is interesting to me and possibly to my co-authors. At this point, it might be quite useful to just work out what sort of applications interest you in the room. Largely your actuaries. Who here deals with work that is created by Solvency II in insurance? What would you say? Maybe not as much as a third. Who here deals with work that is created by the Basel regulations in banking? Okay, even less. Actually, I need to think of some other lines of work, actuaries, but I don't know who. Yeah. And a lot of you are PhD students. So, well, depending on whether you're interested in solvency or Basel, of course, there are different time frames that are natural. So in solvency, you're supposed to be looking at annual loss distributions and computing a solvency capital requirement based on annual losses. But I think when you model the way that risk factors behave, you still want to build up your knowledge of how risk factors behave by modeling at a lower frequency, perhaps monthly, maybe weekly or something like that. In banking, of course, short time intervals are of interest. There was hardly any hands went up when I asked about interest in Basel work, but certainly for the trading books of banks, the canonical time horizons are either 1 day or 10 days. And so they're interested in the kind of changes you observe at those frequencies. But I think even for Solvency II work, when you model these kinds of risk factors, I believe it's better to be modeling at a higher frequency than trying to simply model annual changes where you don't have so much data. Okay.
Well, but the extrapolation again to a 1 year would be difficult then. You can do it in the framework of Brown motion, but then you're back in the normal world. The world is not normal.
Yeah, or you can simulate, we can fit some time series models and we can simulate their consequences over 1 year. I mean, build scenario generators, perhaps. Not easy to get a picture of annual changes in fundamental. It's not easy to risk factors. But
We did once with a student of mine, Kaufman, an analysis for Swiss Re, estimating risk measures for yearly data, and there are a lot of comparison of various models. There we said, well, use monthly changes, model monthly change, and then do a square root of 12, which I know is, again, Brownian scaling, but that in a lot of study, that turned out to be a fairly good way, a very pragmatic way.
So simple scaling laws, but also simulations of the kinds of time series models we'll get onto might be worth thinking about. So if it's a risk factor, if it's a risk factor change, it will be X. If it's a risk factor itself, it will generally be Z, although later on we'll have some innovations which are called Z. But generally the X's are risk factor changes. And for a price, the typical risk factor would be a log price, and so the risk factor change would be a log difference. So in R, when I did diff log, those were logarithmic differences. That was computing this, the logarithmic difference of prices. And the logarithmic difference of prices, at least over small time intervals, is not so different to the relative difference in prices. So for small time intervals, they are quite close. But generally, by default, we will take log returns. So what are the stylized facts? Well, one of the things we saw very evidently in a lot of those time series of log returns was volatility clustering. This is an old example that we've had in the textbook since the first edition, the DAX index in Germany, 1985 to 1994. We had it in there because you can tell a story, a historical story around most of those periods of volatility. For example, this volatility here in late 1987, and this volatility here in, this would be very late 89, and then this extreme value here in 91, were related to political. That's the fall of the Berlin Wall. That's the putsch in Moscow in the time of Gorbachev. And that was the Black Monday events on the stock market. But you see volatility in some of these periods. What is volatility? I mean, it's periods of large changes in value, often with rapidly alternating signs. So it goes up, it goes down, it goes up. But the magnitude of the change is large, and you tend to get large changes followed by other large changes, although not necessarily of the same sign. If you simulate independent data, you're never going to get that. So there are two simulated time series here. The simulated time series are of the same length as the real time series, and moreover, they are statistically fitted, or they are from models that have been statistically fitted to the real data. So fit a normal distribution to that, and then simulate the fitted normal. And of course, you get something that looks nothing like the original. The scales are the same, so it simply can't fill out this white space in the same way that the real-time series does. So fit a student distribution. If you fit a student distribution, you have three parameters to estimate. You have a location, you have a scaling, you have a degree of freedom that controls the weight of the tail, and you get something that begins to look like it at least kind of explores the same range of values. But neither of these two contain volatility. They're independent data. You don't get the clusterings of large changes followed by if you like, the clusterings of small changes. You don't see that. So I think I've said everything here. The simulated normal data, too few extremes. The simulated T data, that's the degree of freedom, a better range of values, but no volatility clustering. So whatever time series models we use to describe time series like the first one, somehow they should attempt to reproduce this volatility clustering. What else? Now, I'm going to talk about autocorrelations before I actually define them. They come in chapter 4, but who's familiar with ACF plots? Again, it's maybe 50%. So what's an ACF plot? This is a picture of the estimated serial correlation structure, basically. And so what you have on the x-axis, it's called lag. And a lag of 1 would mean the estimated correlation between returns on day t and day t plus 1, or returns that are separated by 1 day in time. So that would be a lag 1, and obviously a lag 3 would be the correlation. We would be looking at the correlation between returns on day t and day t plus 3. And we estimate the magnitude, and we draw a vertical bar. And basically, you can't see anything. There are little notches here, but these vertical bars are very small. In fact, they lie between 2 dotted lines. What you actually see here is estimated serial correlations which are very, very small. In fact, not significant at all. And that is common for all 3 time series. It's the same 3 time series. I think I'm having a problem with the pointer. It's probably a battery. Ah. Can we edit that? Oh well. Switch it on.
Oh no, that's your computer, right?
Yeah, too many pointers. Well, there's old-fashioned technology. So these are the 3 time series in question. And these pictures here on the left relate to those 3 time series. So you see, I can use the laser pointer at least, you can see DAX, normal T. Basically, you see 0 evidence of correlation within these time series, the real data and the independent data. Now, the independent data, there can't be any correlation. They're independent. Independence means no correlation. But then you see something very interesting, which is you take the absolute values. So you remove the signs and you take the time series of absolute values, the magnitudes. And then you see a lot of correlation persisting to actually quite high lag. So this is telling you that there is estimated correlation between the absolute values of these time series data. And that's consistent with the idea of volatility clustering, where large values are followed by other large values, although not necessarily of the same sign. But again, for the independent data, you see nothing. Because it doesn't matter what you do to the independent data. You can square them, you can take absolute values. You're still not going to create serial dependence. They're still going to be independent. So it's the difference between this picture and this picture, which is the signature of a real financial time series, whereas this is what independent data do. So I think I've said everything here. ACF stands for autocorrelation function. In fact, these are estimates of the autocorrelation function. Non-zero ACF at lag 1 implies a tendency for a return to be followed by a return of equal sign. Not the case here, but this shows a tendency for a return of larger magnitude to be followed by another return of larger magnitude. Okay, there are other tests we can do on this. There are other tests of serial dependence which are based on the autocorrelation function or the estimated autocorrelation function. They often go by the name of Ljung-Box tests or related tests which you can use to test the dependence structure. Let's move on to the next stylized fact.
What's the GVM?
Geometric margin. Oh yeah, I'm not going to say everything on every slide, but do stop me if there's something which looks interesting. For an IID process, you would expect what's called the autocorrelation function to be the 0 function, or rather the indicator function for H is 0. You're just going to have a spike at 1 and then 0. That's not the case here in the real data. It's not the case. It is the case here. It looks like it is the case here, but not here. So what can we say? We can say that because these are not consistent with independent returns, that means that the risk factor is not consistent with a random walk, or if you like, the price process is not consistent with a geometric Brownian motion. Okay. Other things we can look at. We can look at the extreme values and how they cluster. This is a graph that I've always quite liked. or an exploratory method, draw a kind of high threshold and pick the largest observations, either the largest positive ones or the largest negative ones. I think here we've taken probably the largest down movements, if I remember rightly. We've taken the largest down movements, but we've made them positive. And look at the gaps between them. Now, the theory says, this really belongs, I think, in the extreme value theory chapter coming up tomorrow. The theory says that if you have a process of independent data, then when you look at the extremes, so you draw a high line, maybe you take the top 10% of values or the top 5% of values, but in the limit, as you take a higher and higher threshold and just look at the largest observations, what you get in the limit is a Poisson process. And what we know about the Poisson process is that the waiting times between extremes are exponentially distributed. So that's the reason that we look at the extremes and we look at the spacings between them and we compare them with an exponential distribution. That introduces the subject of the QQ plot. Actually, the theory, the sequencing is a little bit out here. The theory will come later, but let's just say informally what a QQ plot is. Again, probably there are people here who haven't encountered it and many who have, but in a QQ plot, we compare data against a reference distribution. We compare the quantiles of data against the quantiles of a reference distribution. And what we're looking for is a straight line. So what I do is I compare the spaces between extreme events, I order them, and I compare those spaces against an exponential distribution. And if I have exponentially distributed spacings, I should see a straight line of points, which I don't see. But if I repeat the same experiment for independent data, I do see this kind of straight line pattern. Well, it's never going to be perfect, but for IID data, the process of extreme values converges to Poisson with exponential spacings. For real data, it doesn't. That's another stylized fact. The DAX data shows shorter and longer waiting times. Okay, so what about distribution? Well, real data, real log return data, certainly for daily log returns, weekly log returns, monthly log returns, and there are some nice scripts in the repository that confirm this empirically, it's not going to be normally distributed. Maybe by the time you get out to quarterly log returns or annual log returns, but once again, we don't have a lot of data, you're getting more normal because you're adding up more and more higher frequency returns, and so there's a central limit effect. But for daily, weekly, monthly, you can demolish the idea that they are normally distributed. They're not. And this slide just has a whole list of tests that could be carried out, and which indeed are carried out in one of the scripts in the repository that I'll show you in a sec. Well, I'll show you where it is. We won't go through that one in particular. But we have lots of tests of normality. We have some tests which are not specific to normal. They are general tests of a set of data against a candidate distribution. And quite often they are constructed through the empirical distribution function that Marius has essentially defined through a picture here. And then we have some plots that are specific to some tests which are specific to the normal distribution. One that I often default to is Yark-Bera, because it's a test that simultaneously compares the skewness and kurtosis of data with that of a normal distribution. Sort of it jointly compares skewness and kurtosis and tests against a chi-squared distribution. So another stylized fact is that financial data are not normal. I mentioned QQ plots. These belong to the realm of graphical tests. there are two varieties, PP plots, which are probability plots, and QQ plots, which are quantile plots. They are based on the order statistics of the data. That is, you have a data sample of size n, you order them from smallest to largest, and these order statistics contain all the relevant information about the data. From them, you can get the empirical distribution function as well. And the PP plot is a comparison basically of theoretical probabilities with empirical probabilities. The one that we will most often use is the QQ plot. So let's just talk about that one. We compare theoretical quantiles of a reference distribution with empirical quantiles of the data. So the order statistics can be thought of as the quantiles of the data. And they should correspond to the quantiles of the reference distribution if that distribution is a good fit, if you like. What is PI here? PI is the plotting point. Should that be an equality, the first one? I minus 1/2 over n, let's say, I minus 1/2 over n, or some little correction. That's what PI is, because this should correspond roughly to the I minus 1/2 over n quantile. Or rather, sorry, this should correspond roughly to the I minus 1/2 over n quantile. Anyway, it's easier to look at the picture and to learn how to interpret it. Let's just look at the pictures. So you do this kind of thing. There's Walt Disney. There's the quantiles of a reference distribution, normal. And here are the plotted against the ordered sample, the order statistics. And what you typically see is an inverted S. You see an inverted S, and that is the sign that you're dealing with data which tend to have bigger quantiles than the reference distribution. For location scale families, you can basically use the standard form of the distribution. You don't have to fit it so that you get the best estimate of mu and sigma. You can just plot it against quantiles of the standard normal for a location scale family. This is a little experiment with simulated data from a T3 distribution. So you have, if you like, well, you have red dots and black dots. And so the red dots, this is the QQ plot of the data against a normal reference distribution. You see the inverted S in the red data, just like this. You see the inverted S. Now, the true distribution of those data is actually T3. And so the other quantile plot, the black dots, is a QQ plot against T3. And theory says it should be linear, but you're never going to get perfection when you're dealing with a heavy-tailed distribution. These largest values can be quite erratic, and so you have to learn a little bit what a good QQ plot looks like, particularly when you're dealing with a heavy-tailed reference distribution. Most often we use the normal reference, or in the case of these pictures that you saw before, we use the exponential reference for the spaces. But that's the QQ plot. So let me summarize the stylized facts, the one-dimensional stylized facts. Return series are not IID. I will assert they are not, they cannot, maybe it's better to say, cannot be modeled by IID, because they are data. And IID is a concept really for random variables, but they cannot be modeled by IID. Although it is true they show little serial correlation. The series of absolute values, or indeed squared values, shows a lot of serial correlation. Your best guess about the expected log return tomorrow is usually 0. It's very difficult to predict the next log return with any great success, although you can have more success predicting the magnitude of the log return, but not the sign. That is a little bit the problem. So I haven't really talked a lot about the third stylized fact, but that belongs to the list. Volatility appears to vary with time. Extremes appear in clusters, and return series are heavy-tailed, or at least heavier-tailed than normal. Longer tails than normal. Also a little bit narrower in the center, which is a pattern called leptokurtic. Okay. Now, in this set of scripts for chapter In this set of scripts for chapter 3, there are a few that you might want to play with. I said there was a script on testing normality. There's a very extensive script testing univariate normality, largely written by Marius, which runs through this arsenal of normal tests and demonstrates that financial data do not appear to be normal. There are some Leung-Box correlation tests, but I thought just to recap what we were saying, what I've been saying, we would run through this script, univariate stylized facts .r. Okay, so we will do this with the S&P 500, the FTSE and the SMI, which we created before. I will just spring on ahead and create the data. So that's our data. And we want to have a look at these stylized facts and just check that they appear to hold for these data. You can immediately see the strong volatility of the Standard & Poor's index returns or the SMI index returns. So, how to get the ACF plot? There is a little function called ACF, which estimates the correlations, but it will do a little bit more. It will actually give you a matrix of pictures. And these ones in the center line here, these are the estimated serial correlations of each of these series. So you'll see that the little bars, those are the estimates. So obviously for the Standard & Poor's, the first estimate at lag 1, I'm trying to hit it here with the laser pointer, is a small negative number, as is the second one, and then you hardly see anything. And so this is estimated serial correlations for Standard & Poor's, for FTSE and SMI. The other pictures are what are called cross-correlation estimates. So these are estimates of the correlation of, let's say, the Standard & Poor's on day T and the FTSE on day T plus 1, or the Standard & Poor's on day T and the SMI on day T plus 1. And on the diagonal here, the first bar is always of height 1, because a correlation of an observation with itself is 100%. Off the diagonal, the first bar is basically just an estimate of the correlation between returns on the same day, whereas the other bars are estimated correlations between days T and T plus H, let's say. So that's the picture you get. And you don't see anything. There's hardly anything happening in these pictures. They are very dull pictures, but then you do the same thing for the absolute values, and you see this. So you do the same thing for the absolute values, and this immediately tells you that you have behavior that is nothing like a three-dimensional IID process. There is strong and persistent correlation. It appears between the absolute values. Of course, you can also get this kind of thing with non-stationarity, which is an issue we will talk about after the coffee break. What else? The weekly. Let's do the weekly. So I made the weekly data before. Take the weekly returns, look at the correlation pictures, you see next to nothing. Look at the weekly absolute values, you see lots of correlations. So there's still an estimated non-zero correlation for weekly the absolute values of weekly returns.
So the lag here is in weeks?
The lag here is measured in weeks, yeah. 1 week, 2 weeks, yeah. Surprising. what about the heavy tails? There's a little block of code here which will cycle through, it'll cycle through the 3 time series, and you'll see it makes a QQ plot. There's a function called, it's standard R, a function called QQ norm, which will make a QQ plot, and QQ line, which will put a straight line on it to allow us to judge whether we're dealing with plausibly normal data. I'll just do it with weekly. Are weekly log returns normally distributed? Not really. You get the inverted S for weekly log returns. And we could do some formal testing. Weekly log returns are not normal. Monthly log returns are not normal, or cannot be modeled by normal. What about the clustered extreme values? Well, there's a block of code that makes that's the picture for S&P, the first index. That's the picture for S&P. We're looking for some kind of straight line here, but we get something that looks nothing like a straight line. So I just repeated the experiment for IID data. So in this block of code here, what we do is we simulate student T distributed data. I'll just draw your attention to RT. RT gives you a random sample from a T distribution. The degree of freedom is 5, and it makes a random sample that is the same length as the true data. And then we pick out the extremes, we plot them. Well, actually, let's do it in, yeah, I perhaps should have done this in 2 pieces. So this is independent data. Those are the extremes. We've picked out the top 100, if you like, the 100 most extreme. And then we look at the spaces between them and do the QQ plot. And you get something which is more plausibly a straight line, whereas perhaps I should go back to the real data. Perhaps this is the best order. Those are the extremes of the real data. Here's 2008 again. Nothing happened in here, nothing happened in here. Those spaces are not exponential.
How would you calculate 5 degrees of freedom?
I just picked it. I picked something which is relatively small, but not very small. It doesn't really matter because this has got nothing to do with the tails of the distribution and everything to do with the fact that I was simulating independent data. If I did it for a normal, it would be the same. Yeah. So there's a script there that tries to illustrate these univariate stylized facts. Now, you'll have seen that there are also some multivariate stylized facts here, but I'm not going to go through these at this point. I may come back to these tomorrow when we talk about multivariate time series, but there are just some observations on these pictures we've seen. These are called, this picture here, one of these is often called a correlogram. A picture of estimated correlations. And this is called a cross-correlogram between 2 time series. And so once again, you see nothing much happening in these pictures. All the little bars are close to 0. And I'll talk exactly about how this picture is formed. But when you go to the absolute values, you see that they are not so negligible. So the final thing, if you'll give me 1 minute. Wait, I go.
Sorry.
Yeah, please, yeah.
On all those plots, you showed these two red dotted lines.
Yeah.
What do they represent?
Yeah, so it's a confidence interval for these correlation estimates. And the theory says that if you're dealing with IID data, then 95% of those bars, so 19 out of 20 of these bars should lie between the red lines. Yeah. And I just wanted to end with one picture because, again, this hints at the direction that Marius and Paul will be going tomorrow. Back to BMW and Siemens. Here's the history. So I think we looked at, what did we look at? Well, we looked at the DAX before. We looked at the DAX index before, but these are 2 returns from the DAX index. And we've been showing this for about 15 years. It's an old chestnut, if you like, because it seems like ancient history now. So you can trace some of these extreme values back to political events in Germany and in the Soviet Union of the time. If you do the pairwise scatter plot, you see this, and you see that, in fact, the 3 most extreme days are down here. That's day 2, fall of the Berlin Wall, or, well, actually, no, not quite, because, of course, that took place over a period of time, but a certain significant day at that time is day 2. Day 3 is the coup. Day 1 is Black Monday. But you see them all down here in the joint left tail. And a question for us is going to be, what kind of models can capture this tendency for the most extreme values to occur together in a statistical way? Because really, of course, what we're trying to do is get a distribution that describes these events, the occurrence of these extreme events. And this phenomenon here of the most extreme events sort of occurring together in the tail, we call it tail dependence. And quite often when you look at several time series, you see this. You see that the most extreme events kind of occur together. They occupy these positions in the lower left tail, sometimes in the upper right tail, and you get a very pointy tail. You see this is a very pointy tail because of that. We need models that can reproduce that sort of behavior if we are to model the dependencies between extremes. And that's just a little hint at where the story goes tomorrow. Okay. Any burning oh, sorry, I think Francois, do you have something to say? No. But any burning questions? You'll get a bit more of me after the break, so you can store them up.